Welcome, everyone. I'm excited to kick off today's session with a presentation on derivation. This is the first slide, which is our cover slide. Today, we'll explore the fascinating processes behind derivation, understand its significance, and see some practical examples. So, let's get started and dive into the world of derivation together. Let's take a quick look at the contents of today's presentation. We'll start with the fundamentals, such as the definition of derivation, which is essentially the process of finding the derivative of a function. From there, we'll explore key rules like the power rule, quotient rule, and product rule. These are essential tools for calculating derivatives efficiently. We'll also delve into how derivatives are used across various fields, like in chemistry, biology, physics, and even business, to understand rates of change and other dynamic phenomena. For example, in physics, derivatives help us understand motion, while in business, they assist in optimizing profits. Additionally, we'll touch on the history of how derivatives were developed, highlighting contributions from figures like Sir Isaac Newton and Sir Leibniz, both of whom played pivotal roles. Finally, we'll look at some real-life applications, from radar guns in speed detection to automobiles and even scientific experiments. Throughout the presentation, you'll see how these mathematical concepts are not just abstract ideas, but practical tools that impact many aspects of our daily lives and various sciences. Let's take a closer look at derivatives, starting with their rules and some practical examples. These rules are the foundation for understanding how functions change and are essential for solving many real-world problems. We'll see how to apply these rules through various examples to strengthen your grasp. Moving back in history, the development of derivatives has a rich story that highlights their importance in mathematics and science. We'll explore this history to see how the concept evolved over time. Finally, we'll discuss the many applications of derivatives, from physics to economics, demonstrating why mastering these concepts is so valuable. Throughout this slide, keep in mind that derivatives are all about understanding change, and these tools help us analyze how things vary in a precise way. Let's explore the concept of derivatives. Essentially, the derivatives of a function represent an infinitely small change in the function with respect to one of its variables. Think of it as zooming in so closely that you can see how tiny variations in input affect the output. This is why we often call the derivative the instantaneous rate of change. Geometrically, the derivative is the slope of the curve at a specific point. So, if you imagine a curve on a graph, the derivative tells you how steep that curve is right there and then. Most importantly, the derivative gives us the exact rate at which one quantity changes relative to another. This idea is fundamental because it allows us to understand and predict how systems evolve over time or change in response to different variables. Now, when we talk about the definition of derivation, we're really focusing on understanding this concept deeply. It's not just about the math, it's about grasping how small, almost infinitesimal changes impact the behavior of functions in real-world applications. Let's clarify a common misconception. When we see di and dx in calculus, they don't actually mean d times y or d times x instead. Di and dx are different concepts. They represent infinitesimally small changes in y and x, respectively. It's easy to get confused because of the notation, but understanding this distinction is crucial for grasping derivatives and slopes. Remember, di over dx isn't a simple multiplication. It's a ratio of these tiny changes, which helps us analyze how y changes in response to x. So, always keep in mind, di and dx are not multipliers, but symbolic representations of these minuscule differences that form the foundation of differential calculus. Now, let's delve into the history of the derivation. Understanding how this concept has developed over time really helps us appreciate its significance today. We'll look at the key milestones that shaped its evolution, starting from early foundational theories to more recent advancements. These historical insights demonstrate how the idea has been refined and expanded through ongoing research and discovery. By exploring this background, we can better grasp the underlying principles and appreciate the context that has led us to our current understanding. This story of development is closely tied to the overall theme of progress and innovation in our field, showing how each step built upon the previous ones to reach where we are now. Let's talk about Sir Isaac Newton, one of the most influential scientists in history. Newton's work fundamentally changed our understanding of the universe. He's best known for formulating the laws of motion, which describe how objects move and interact. These laws are still the foundation of classical mechanics today. Newton also made groundbreaking contributions to gravity, explaining how objects are attracted to each other with a force that depends on their mass and distance. His work not only revolutionized physics, but also connected to the broader theme of scientific discovery and the pursuit of understanding the natural world. Newton's insights laid the groundwork for many technological advancements we benefit from now. So, his contributions are truly a cornerstone in the history of science. Now, let's turn our attention to Sir Leibniz, a fascinating figure in the history of philosophy and mathematics. Leibniz was not only a brilliant thinker, but also a true polymath who contributed significantly to various fields. One of his most notable achievements was co-developing calculus independently around the same time as Newton, which revolutionized how we understand change and motion. Beyond mathematics, Leibniz was deeply interested in metaphysics and logic, striving to create a universal language of reasoning. His idea of a pre-established harmony between mind and matter is particularly intriguing, as it ties into the broader theme of interconnectedness that runs through this presentation. Leibniz's work exemplifies the pursuit of knowledge through both innovation and collaboration, reminding us how diverse perspectives can lead to groundbreaking ideas. So, in the context of our discussion, Leibniz's contributions highlight the importance of intellectual curiosity and the quest for understanding the fundamental principles of our universe. Let's take a closer look at this slide. Here, we're emphasizing the key points that tie into our overall theme of effective communication. First, it's important to recognize that clear messaging is essential for engaging our audience and ensuring our ideas resonate. Next, we see how adapting our language and tone based on the audience can make a huge difference in how our message is received. We also want to highlight that consistency is critical. Whether in branding, message, or delivery, it builds trust and credibility over time. Finally, I want to stress that actively listening and responding to feedback closes the loop, making our communication more dynamic and effective. All of these elements together reinforce the importance of intentional, thoughtful communication strategies, which ultimately drive our success. So, in an automobile, you'll always find an odometer and a speedometer. These two gauges work hand in hand to give the driver essential information. The speedometer tells us how fast we're going, while the odometer tracks the total distance traveled. Now, what's interesting is that in modern cars, these are often electronic. Instead of mechanical parts, they use electronic signals. These signals come from sensors in the tires that measure rotation. The electronic system then uses derivatives, basically mathematical calculations, to convert this data into miles per hour for speed and total distance in kilometers or miles. This integration of electronics makes the gauges more accurate and reliable, which ties back to the overall theme of how technology enhances everyday tools. Let's connect this to our automobile theme from the previous slide. All police officers who use radar guns are actually making use of derivatives in a very practical way. When a radar gun is pointed at your car on the highway and fired, it can determine the time and distance at which the radar hits a specific part of your vehicle. By applying the concept of derivatives, the radar gun can calculate how fast your car is going. That's the speed, and also report how far your car was from the radar gun at that moment. Essentially, derivatives help convert the measurements of time and distance into a meaningful speed reading. So, in a way, these radar guns are relying on the mathematical principles we've been discussing to do their job accurately and efficiently. In the business world, derivatives have many practical applications. One of the most important is when you're working with data that's been charted on a graph or organized in a data table, like in Excel. Once you input your data, you can create a graph to visualize it. Using derivatives, you can then estimate key points, such as the profit and loss threshold for specific ventures. This allows businesses to make more informed decisions by analyzing how their data behaves and predicting outcomes. Essentially, derivatives help translate raw data into actionable insights, which is crucial for strategic planning and risk management in any business setting. Let's take a look at how different fields relate to mathematics, specifically calculus. Economics relies heavily on calculus, which is reflected in its score of 3. This is because calculus helps in understanding concepts like optimization, cost minimization, and modeling economic systems. Moving on, mathematics itself has a score of 5, highlighting its fundamental role across all sciences. Biology, with a score of 2, uses calculus especially in modeling population dynamics and enzyme reactions. Chemistry, scoring 4, employs calculus for reaction rates and molecular modeling. Lastly, physics, with a score of 1, is deeply intertwined with calculus, as it forms the basis of understanding motion, energy, and fundamental forces. Overall, these scores show how calculus serves as a crucial tool across diverse scientific disciplines, connecting theory to real-world applications. Now, let's delve into how derivatives play a crucial role in understanding motion in physics. When we talk about the displacement of a moving body, the derivative of that displacement with respect to time gives us the velocity. Essentially, this tells us how quickly the position is changing at any given moment. Moving a step further, the derivative of velocity with respect to time is acceleration, which indicates how the velocity itself is changing over time. These relationships are fundamental because they link the concepts of position, velocity, and acceleration seamlessly. Building on that, Newton's second law of motion provides a broader perspective. It states that the derivative of the momentum of a body equals the force applied to it. This means that force is directly related to how momentum changes, which ties back to acceleration since momentum is mass times velocity. So, in essence, derivatives are the mathematical tools that help us quantify and understand how objects move and respond to forces. They are central to connecting the physical quantities we observe to the underlying laws governing motion. Let's take a closer look at this equation. dn/dt equals n0 times 2 to the power of t, multiplied by the natural logarithm of 2. This tells us how quickly the population is growing at any given time t. The key idea here is that the rate of change, or how fast the population is increasing, depends on the current population size, which is modeled by nt, equals 2 to the power of t times n0. In the example of bacteria doubling every hour, we see that the population doubles at each time step, starting from an initial population n0. While the instantaneous rate of change makes perfect sense in continuous models, in real life, populations often grow in discrete steps, like these bacteria doubling. However, when populations are large, we can approximate their growth with smooth, continuous curves. This allows us to use calculus tools, like derivatives, to analyze and understand growth patterns more effectively. So, the main takeaway here is that derivatives help us quantify how populations grow over time, especially when the growth is exponential, and this plays a crucial role in biological modeling. Now, one interesting application of derivatives in chemistry is when we need to find the concentration of a specific element in a product. Derivatives help us calculate how quickly a reaction occurs, which is known as the reaction rate. They also play a crucial role in understanding properties like compressibility, which is important for studying gases and liquids. By using derivatives, chemists can analyze and predict how reactions behave under different conditions, making these tools essential for advancing chemical research and practical applications. This connects to our overall theme of how calculus, especially derivatives, provides powerful insights into the dynamic world of chemistry. Now, let's move on to slide 17, which covers some important applications of derivatives in mathematics. First, we see monotonic functions. These are functions that are always increasing or decreasing, and understanding their behavior helps us analyze how functions change over an interval. Newton's method is another key concept here. It's a powerful technique for finding roots of equations efficiently by using derivatives. Next, we have concavity and curve sketching. Recognizing where a function is concave up or down allows us to sketch its graph more accurately and understand its shape. We also touch on the mean value theorem, which guarantees that, under certain conditions, a function's average rate of change equals its instantaneous rate of change at some point. Lastly, the topic of extreme values of functions is critical. These are the maximum and minimum points that help identify the function's highest and lowest values within a specific interval. All these concepts are interconnected and form the foundation for analyzing and understanding the behavior of functions in mathematics. Now, let's move on to slide 18, which is all about the rules of derivatives. Here, we'll go through the key points to help us understand how derivatives are computed. Think of these rules as the building blocks for differentiating various types of functions. They're essential because they make the process quicker and more systematic. First, it's important to remember that these rules apply broadly, whether you're dealing with polynomials, products, quotients, or compositions of functions. We'll look at examples of each to see how the rules are applied in practice. The main idea is that once you know these rules, you can approach any differentiation problem with confidence. They connect directly to our overall goal of mastering calculus and understanding how functions change. So keep these rules in mind. They're your toolkit for differentiation. Now, let's take a look at some examples to see how the quotient rule works in practice. The quotient rule is a powerful tool when you need to find the derivative of a function that is expressed as a division of two other functions. It tells us that to differentiate a quotient, we take the derivative of the numerator times the denominator, minus the numerator times the derivative of the denominator, all over the square of the denominator. This rule is especially useful when the functions involved are complex, or when simple algebraic manipulation isn't straightforward. Remember, the key is to carefully apply the rule to avoid mistakes. As we move forward, you'll see how this rule simplifies the process of differentiating complicated fractions, tying back to our overall goal of mastering derivative techniques efficiently. Now, let's wrap up with the chain rule, which is a fundamental concept in calculus. The key idea here is that when you're differentiating a composite function, meaning a function inside another function, you need to consider how the inner and outer functions change. Think of it as a way to chain derivatives together, hence the name. The most important concept to remember is that you take the derivative of the outer function and multiply it by the derivative of the inner function. This rule allows us to handle complex functions that are built up from simpler ones. Connecting this back to the overall theme, mastering the chain rule is essential because it enables us to break down complicated derivatives into manageable steps, which is crucial for advanced calculus and real-world problem solving. So, understanding and applying the chain rule effectively truly unlocks a lot of the power of calculus.